Professor, Associate Professor, Doctor, and to all the audience. I hope everyone can hear my voice clearly.
Yeah, clear.
Okay, so I would like to welcome everyone and the speakers to our second SDG conversation series webinar, and this is actually our second collaboration on SDG conversation series with Universitas Tanjung Pura after the first SDG webinar that we had on the 26th October last month. My name is Faiza Pardi from Institute for Biodiversity and Sustainable Development, and I will be your moderator for today's session. And today we will have a sharing session with the two speakers first, and then followed by Q&A and also discussion at the end of the session. Should you have any questions or comment or anything that you want to discuss, feel free to send it through the chat zone, and also we will get to as many as possible at the end of the session. Yeah. I would also like to note that the attendance link will be given later after all the speakers complete their presentation. So we have two attendance link, one for UiTM staff, as usual for registration and training hour, and another one for participant outside from UiTM and also from other organization, and for all students as well, in order for you to get your e-certification. Okay, so this webinar actually shows our commitment and also UiTM commitment, of course, in addressing the United Nations Sustainable Development Goals. So we have 17 Sustainable Development Goals with 169, if I'm not mistaken, to form the core of the 2030 agenda. So it balances the economic, social, and also ecological and environmental dimension of sustainable development. So last webinar, we have covered 3 SDGs. So for today, we hope to cover another 2 SDG, which are SDG 3 and SDG 9. SDG 3 on promoting healthy lives and well-being at all ages, and SDG 9 on resilient infrastructure to promote comprehensive and sustainable industrialization to foster innovation. And today we are very fortunate to have an expert in the field of chemistry who will be sharing with us the beauty of chemistry in the hands of scientists and why does it matter to us. So our two speakers are Associate Professor Dr. Risa Nofiani from Universitas Tanjung Pura, Kalimantan, who will talk on the exploration of secondary metabolites from microorganism, and Dr. Agustono Wibowo from University Teknologi Mara Jengker campus, who will share on the importance of synthetic chemistry in the pharmaceutical industry. Again, I would like to express our thanks to Dr. Risa from far from Kalimantan, yeah, and also Dr. Agus from UiTM Jengker for accepting the invitation and making your time to be with us today. So before we begin, allow me to introduce our first speaker today, Associate Prof. Dr. Risa Nofiani. She is a lecturer of biochemistry at Department of Chemistry in the University of Tanjung Pura, Indonesia since 2000. She received her Bachelor of Science and Master of Science degree in Chemistry from University of Riau and Bandung Institute of Technology Indonesia respectively. And then she continued her education with a PhD degree in Chemistry from University of Bristol, United Kingdom. She got a visiting scholar at Michigan University, funded by United States Civilian Research and Development Foundation, and Oregon State University, funded by DICTI-funded Fulbright grants for Indonesian lecturers. Her research focused on drug discovery and biosynthesis from microorganisms using various approaches like bioinformatics, omics, and also molecular biology. And also she focused on traditional food processing. So I think this is a good subject in which all of us would be deeply interested because secondary metabolites have shown a great potential for human and animal health, with significant potential to be used in medicine. Although many reports on the secondary metabolites have been published in recent years, but our understanding to enhance the production of bioactive secondary metabolite is still limited. So to elaborate more on this topic to all of us today, please join me to welcome Associate Professor Dr. Risa Nofiani to present on the exploration of secondary metabolites from microorganisms. So please welcome Dr. Rifa.
Okay, thank you, Dr. Faiza, to introduce me for this seminar. I'm very Hannah actually. So, okay, for today, I would like to speak about some project about the exploration of secondary metabolite from microorganisms. But before we started, I want to introduce um, my university first. This is my university. Is very welcome from UITM to visit in our university because we close actually with the East Malaysia. So West Kalimantan is resided below Kuching. So please welcome and to make good collaboration for in the future. Okay, why so interesting about secondary metabolite? Secondary metabolite are compounds produced by organisms which are not directly involved in the normal growth, development, or reproduction. But many secondary metabolite is important for human being because have various biological activity that we can use for drug or medicine. For example, my project is focused on fungus and bacteria. Some fungus we have already known about the penicillin that is very important drug. Until now, we can still use this drug is from penicillium fungus, fungal penicillium. And the other thing we have already known about the uh, glycofulvin or streptomycin, all of them we can isolate it from bacteria, particularly actinobacteria. So this is the picture show you about the fungus in the right hand, and the left hand is one of actinobacteria. In our group, we use two approach to get secondary metabolite. The conventional method we use, like we try to isolate it as many as bacteria from a source like mangrove or marine. So we try to isolate it as many as possible, and after that we grow in the lab and do some extraction and do like biological activity. But the conventional method now little bit less efficient because some compound that we isolated if have already known, so it look like wasting time, wasting money. If we use we use approach this method. But however, in our lab, we still try to do that, but we still like improve using different medium and do some co-culture. We try to do some extraction, and we'll see about the secondary metabolic profile from this extract using the SPLC. But however, it's very difficult now because sometimes our target, the concentration is very low, so it's very difficult to elucidate the structure. Now, the second approach in my research we start to do sequencing the whole genome of our bacteria, and after that we try to find potential biosynthetic gene cluster, and after that we try to do some genetic engineering like knocking out, or we try to put some gene target to another host. Hopefully we can get new compound, because many bacteria or fungus cannot produce all of the secondary metabolite in the lab. So we call it a silent gene. So for this approach, we try to induce silent biosynthetic gene to express in the lab, in our culture. We have already started to collect some microorganism from many sources like mangrove, and we start to collect some microorganism from pig, because unfortunately many burn forests now, so we cannot get the indigenous microorganism, unfortunately. So we moved to marine, and we have already collect some marine bacteria from many islands around West Kalimantan, like Lemukutan, Randayan, Penata Island. And we have already, some of them we have already started to do screening for the activity. This is the collection we got from our source. In the lab, we got some fungus. In the lab, we got some fungus like LP1, R1, and the right hand, this is some actinobacteria that we collect, and it's very interesting. You can see the colony is very wide range variative, and we try to identify some actinobacteria from there. And you can see from the phylogenetic tree, some of them see a little bit different with both between them. And in the below, you can see in the below like RS6, RS4, RS1, 5, 7 is look like similar from the phylogenetic tree, that we can use 16 srRNA gene. And if we see the pairwise identity of the 16 srRNA gene of each solid, for example, from phylogenetic it look like similar, we can see the percentage of identity almost 100%. For example, RS7, RS1, 5, and 6. But if we look from the colony, they look very different. So we need and do some biochemical tests. We'll see some difference between them. So for further identification, we need to do like how amplify the housekeeping gene to do some more identification. And if necessary, we can do like use the whole genome sequence for the identification. what we can do after that, for the conventional method that we use, we try to use different medium to induce a silent biosynthetic chain cluster to produce antibacterial. So we use this one, three medium, MB with the artificial seawater, ISP1 with the artificial seawater, and TE and EM medium. So from this table, we can see, for example, RC4, we can see MB medium and ISP1 medium is look like similar, even though the activity is look better using the MB medium. Even though all of the medium that we can use are showing the same activity, And what we can do the next to induce the antibacterial production, we try to do some co-culture using the Mycobacterium smegmatis. We can see the culture in the left, and using the EM medium, and the second one we using Mycobacterium smegmatis and GP1 isolate using the same medium, and the second one is control GP1 isolate. So we can see from this co-culture using the Mycobacterium smegmatis induce pigmentation from the culture, especially GP1. But we don't know can induce the antimicrobial activity more better or not. I don't know. We'll see later. From our result, it look like Mycobacterium smegmatis cannot induce the production. If we can see the ball RS2 and using the Mycobacterium smegmatis, it look like the best way because not significant different. We can use only EM medium to grow RS2 compare if we do co-culture. And we have already tried, because our experience, sometimes we have already isolated compound from the extract, and after we isolate it, do some elucidation, the structure, we can get the known compound. Before we do isolation, we try to analyze the extract, the potential extract. Now we use our R3 and RC4 to do some like metabolite analysis. So we run the sample into LCM, high resolution mass spectrometry, and after that do some analysis using the GNPS platform. From there we go the main peak 1277, and they are the same between both extract. It look like actinomycin D. This is known compound. So we, even though this is look like the main peak, and the second one 1291 derivative actinomycin, but we find 1263 and 1293 undescribed actinomycin. Maybe this is novel compound. So for this data, we can focus to isolate the compound for this 1230 and 1293. hopefully we can get a novel compound. But this is a good answer. So for previous slide, for this isolate showing the very good activity, very good antibacterial activity, maybe this is from actinomycin D. The other approach we use, because we try to do some sequencing for some bacteria. We sequencing the whole genome using the short read and long read. For example, from this data, we can see Streptomyces RS2 have very potential bacteria to produce novel compound like this one. We can see hebocdiene, polyketide have similarity only 8%. Maybe this one, if we successful to isolate, maybe we can get the novel compound. Or we try, and from this data, we try to do some knocking out for this gene cluster, so we can choose especially a polyketide group to do some genetic engineering. Hopefully we can get good, the secondary metabolite. Now, the other thing we can do from the whole genome sequence, we try to elucidate the biosynthetic pathway. For example, strobilurin. Strobilurin is very important compound because until now we still can use this compound for agriculture because have a fungicide activity. So the first strobilurin isolated from decay fine, and after that we got got Strobilurus tenacious. Strobilurus tenacious produce the main product, strobilurin A, but strobilurin A showing the fungicide, but is not stable in the light. So many scientists try to do organic synthesis like azoxystrobin. No, this compound can use to remove powdery mildew. But this is very interesting, the compound, because fungus, especially polyketide synthase, very rare to use benzoyl as a starter. But this fungus using benzoyl as a starter. So that's why we try to use the whole genome sequence. We elucidated the genome sequence. We try to do some genome sequencing for this fungus. The first Strobilurus tenacious and the second Bolinia lutea. Why we use Bolinia lutea? Because Bolinia lutea from Ascomycete but still produce strobilurin. And the second one, Strobilurus tenacious, is Basidiomycete, produce strobilurin. So we want to compare between this group from Ascomycete and Basidiomycete and see what it look like biosynthetic gene cluster, and we can see from those fungus there are ST and SL. The biosynthetic gene cluster is look like the same, like this one. And now it's very weird because there are two group fungus showing the similar gene cluster. So after we do some identification and we know Bolinia lutea actually is Strobilurus too. So the previous publication we can confirm they make some false identification. So now we call the name Bolinia lutea as Strobilurus lutea. From this gene cluster, we try to clone gene cluster responsible to make strobilurin, because we know the gene cluster responsible to make fresh strobilurin STPKS1. So we try to clone STPKS1 into Aspergillus oryzae. And after that, we try to fit using the benzoic acid. Using the benzoic acid, the Aspergillus oryzae recombinant cannot produce free strobilurin. But when I fit with the benzoyl snack is mimic coenzyme A, so they start to produce fresh strobilurin with the high titer. 100 milliliter culture can produce 200 mg fresh strobilurin. And we try to elucidate the how to make benzoyl CoA for this fungus, and we try to put some gene into Aspergillus oryzae like STR11, kemudian STR9 and STR10. And this is STR1 means PAL, phenylalanine amylase, non-hem iron oxidase, and coalagase. And from our experiment, they can produce benzoyl CoA, and we can see this recombinant can produce free strobilurin. And after that, we try to learn how to strobilurin A is produced by Strobilurus tenacellus. So we put some another gene, STR9, after the STL2, STR2 and 3, and we can find the recombinant produce strobilurin A and bolinio. I think that's all my presentation. I would like thanks to Prof. Taipo to help me to finish my project, and Jeff Cheng to sequence the whole genome, my actinomycobacteria, and Associate Prof. Benjamin Filmus from Oregon State University to allow me using the high resolution mass spec, and Russell Jacob, my previous supervisor, and my another collaboration, Lars and Salman. Thank you.
Okay, thank you so much, Dr. Risa, for a very interesting presentation, because I'm not a chemist, I'm not in the field of chemistry, but I try to understand. And I think after After listening, yes, after listening to you, I think that you have done a very great job and very diverse method that you explore the conventional and the non-conventional method how to extract the secondary metabolite, right? So what I can understand and conclude actually microorganism have a greatly diversified since many potential secondary metabolites can be pulled out from them, and it plays important roles in the environment as well as being crucial in a series of green processes and cleaner technologies ranging from biogeochemical cycle to various industrial production. And if we use the microorganism wisely, I think they can contribute significantly to the sustainable development, because we know that the common goal of the world now is the use of cleaner production and green technologies. So uh, the I think the method that you use basically, yes, contribute to the cleaner production and green technology, because that is the common goal now, as million people dying each year due to unhealthy environment. Okay, so we have also we have received, yeah, two question I think, and also one question from the participant directly to me. So I will keep it until at the end of the session. So let's move to our next speaker. I hope Dr. Agus is ready.
Okay, ready.
Okay, so before we start, let me brief the next speaker, Dr. Agustono Wibowo from UiTM Campus Chinker. He is a senior lecturer of organic chemistry in the Faculty of Applied Sciences, University Technology Mara, Pahang Branch, Jinka Campus. Prior to joining UiTM Pahang, he was a postdoc fellow at the Institute of Science, UiTM Shah Alam. He received his Bachelor of Science in Chemistry from Halu Olio University, Indonesia, Master of Science from the University of Pajajaran, Bandung, Indonesia, and PhD from the University Technology Mara, Shah Alam. His research work currently is synthesis biological evaluation and molecular docking study of novel pyrrolidine-based immunosugars as a potential alpha-glycosidase inhibitors and anti-cancer agent. And I'm very sure everyone here can wait to listen to another perspective of chemistry and how it can contribute significantly to pharmaceutical industry. Without further ado, I would like to welcome a friend of mine, Dr. Agustono Wibowo, to present his topic on the importance of synthetic chemistry in the pharmaceutical industry.
Okay, thank you very much, Dr. Faiza, for the introduction. I want to share my slide, but this is still off sharing. Can you turn on, please?
Can you share?
Still
cannot.
Offline.
Still offline.
Yes, maybe because I use
yes, because you have two
Yes.
account and then similar name.
The similar name, yes.
Yes, so
The active one is yeah. Okay, thank you.
Okay, all right.
Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good morning, still morning today. I would like to thanks to Prof. Zulkifli for the invitation. Director Institute for Biodiversity and Sustainable Development, IBSD. Today I want to share how important synthetic chemistry in the pharmaceutical industry. This is my campus. I think around 2.5 hours for Kuala Lumpur. Okay, this is a diagram scheme how drug discovery and development processes begin. The first is, I think we can see how the researcher and company develop the drug. Only one drug can have to follow the long steps and spend around 44 million USD only one drug. This is the steps. The first, this is the latest approach in the drug discovery and development. The first, we have to identify the target ID, target validation, and target selectivity. And then we have to study everything about what we want to study. The first, we have to know what we want to study. For example, if I want to study about the anti-diabetic, I want to find antibiotic drug, anti-diabetic drug. So we have to know the target. The target is commonly is a enzyme working to the antidiabetic. For antidiabetic, I study with alpha glucosidase. That's the target. And then after we identified the target already identified, and then we find the target to lead. We find the compound suitable or have activity to that enzyme. We design ad hoc compound library. This is we can download maybe from the library already published, and then we identify new target, support chemical improvement, predict useful properties for the base, and then after validation the target, we move to the lead to the candidate. Target to the lead, maybe we will screen around 5,000 prospect compound, and then we screen until we got the best one. After we got the lead molecule effective, and then we create the support match selection, identify non-expected liabilities. This is for like a toxicity. After pass, maybe we already get the good prospect candidate, maybe 2 or 3 compound. We move to the preclinical development. This is the most active candidate. We choose one, the most active candidate, and then we test preclinical using an animal. In this lead to the candidate, we use in vitro test using cell, line, and culture. And in the preclinical development, we use animal. And then after pass, the drug non-toxic to the animal. This compound is passed because not toxic to the animal, and then we move to the phase 1 first. In the clinical, using human. If the phase 1 is passed, we move to the phase 2. Phase 2, we confirm that the drug is not toxic to human. After confirm not toxic to human, and then you move to the phase 3. This is the last phase before we release the drug. The participant also is bigger compared to the previous one. This is we can use more than 1,000 participant like that. After pass, and then we move to the post-marketing surveillance before we release the drug. We got already active drug for the market. This is the scheme how to discover new drug. If we see here, the time frame for target and targeting validation, we will spend around 1 until 3 years, and then target to the lead, we spend 1 year. So total to develop one drug only, we need around 10 to 15 years. that we spend so much time and money. This is the development. So the development drug is not simple like what we think. And then how to get the active candidate for the drug. For general procedure for obtain active principle from plant, this is the classical method. The classical method, we use plant material for sources of drug. We can use a taxonomy approach. Taxonomy approach, we can see from the, like in Indonesia, we use the jamu, and then we extract the active constituent, and then we analyze, we test to the cell. If active, we can propose to the next assay, like that. And then we can also use a phytochemical approach. Phytochemical approach, we don't care about this species is active or not. We just want to know the chemical constituent, and then we randomly check the bioassay potential. And then we can also using ethnomedical approach. Ethnomedical approach, this one is using we know already that this species is active. Like for example, in Malaysia, I think pokok ketum, we know already the activity, so we can isolate the active constituent, and then we apply to the benefit for the medicinal. And then we can also use information managed approach. This is for library, and then random approach. Random approach is a combination between this all approach. And then for the plant material, and we extract the plant extract. We do the bioassay potential, which compound is potential for the certain assay, and then we isolate. If the assay is positive, we isolate, and then we got the pure compound. Pure compound we analyze with using NMR, and then we elucidate the structure. And then if this compound is the compound isolated from the species is very promising, we can propose the synthesis route, because if we extract from the plant, we have problem because the bioactive compound from the plant is very little, the amount is very little. And then if this compound is prospect, we can do the structural modification. The structural modification, the objective for the structural modification is to increase the activity or to decrease the toxicity, like that. This is the classical approach in the drug discovery. And then this one is using computation method. By using computation method, this is very I think for the budget, if we doesn't have enough budget, this is a good choice, because to develop one drug, we have to spend around 44 million USD. That's a very high amount of money. This one is we can another approach. We can use computation. We use you identify the target selection, and then we design the molecular scaffold selection, and then we screen using virtual screening. Commonly, I think in UITM we use Schrodinger to do this screening. And then the process, all of this process is using a computational, and then we got the potential compound, this potential compound, and then we try to synthesize this active compound. This is from the using from the computational approach. This is a very cheap compared with the traditional approach. Okay, In the traditional approach, we have some problem because for in vitro test and optimization, we need around 10 milligram, 100 milligram, and then in vivo 100 gram. In vivo safety study 1 to 5 kilogram. This is impossible to do to isolate from the plant because this is a very big amount. That's why synthesis is very important in the development of drug. For example, this one. For example, new FDA approved a drug in 2020. Remdesivir. This is active to the COVID-19. This drug is kind of fight COVID-19. This drug is development for this drug is very cheap because this drug is not new drug actually. This drug they prepare this drug for Ebola virus Ebola, but from the clinical study, this drug is not potential for the Ebola, but based on the literature, this compound have activity to the pneumonia disease. That's why after they try to apply this drug to the COVID-19, the result is positive, and FDA approved it as a new drug. This is a total synthesis for this drug. The total synthesis is very simple, only like 5 to 7 root. That's why this one is very possible. We can synthesize this drug maybe until maybe in a ton quantity. Large amount we can synthesize this drug. This is very simple. It's simple drug to synthesize. But another example is this is Taxol. Taxol is an anti-cancer compound. This compound is very complicated because they contain many chiral center, and very sensitive functional groups. This is very difficult. This Taxol is isolated from the year 3 Texas brevifolia. For 1 kilogram pure Taxol, we need around 10 ton free bulk. So you can imagine 10 ton we only get 1 kilogram. Then 1 kilogram only sufficient for 500 patients. The constituent is only 0.011% in the plant. So another problem is Texas species is commonly is a slow growing evergreen or only small tree. This is the problem. If we want to get 1 kilogram, I think we have to chop up around 3,000 tree of the Texas brevifolia. This is our problem. The problem is not only the sources for the drug. That's why this drug is very expensive. In the synthesis part, total synthesis for this compound is very complicated. Synthesis chemists have successfully to synthesize this compound with very selective and very specific control the stereochemistry. The stereochemistry is they control the chemistry is very detailed, and then successfully to synthesize the Taxol. But the problem is the root. The root is very long, and this one is not good for the industry. No good industry. That's why another steps to produce this drug is using the semi-synthesis. Using semi-synthesis, the industry using the analog for the Taxol. The analog is 10-diacetyl-betaine. This one is analog. We just modify the structure and then put these functional groups. The product is done. This This analog we can isolate from also the same species, but in the leaf part, the leaf, and then that's why easier to maintain the tree without to chop the tree. We just wait the tree is grow, and then we harvest the leaf, and then we wait until the leaf is come out again. This is the total synthesis. Okay, the key stage in the synthesis of active pharmaceutical ingredient. This is the step how the organic chemist synthesize active ingredient. The first we have to synthesize, we identify the synthetic route for the compound, targeting compound, and then we have to estimate the cost. Beside that, we also analyze the availability of the starting material. The route, if the route must be shortened, maybe if 1 until 2 route is this is a very good route, because the step is not many, and then we have to see the pattern, because the route is, we have to find this route from the library. We can find from the journal publication or patent. And then we also we have also to analyze the safety assessment, environmental impact, and then reagent, catalyst, and solvent selection, and then design of experiment optimization, stability, and then cost calculation. We have to estimate all of this item. And then this is we have to optimize the design experiments, unit operation, throughput time, robust isolation, crystal properties, and solubility. Industry is preferable if the product can form the crystal, because if the product can form the crystal, we doesn't need to do isolation, because isolation is take time, and the process is little bit difficult. And then we have to analyze the impurity identification. The purity of the compound must be more than 0.05%. Critical parameter, quality issue, process simulation, reactor wash procedure. This one is very important, because if the waste is toxic, we have to consider how to neutralize that waste. And then we have to we prepare equipment selection using batch size, manufacturing cost. This is from laboratory to industry. Material specification, validation, registration. After we successfully synthesize the compound, we have to do the registration. From here, from the lab scale to the industrial scale, until few kilogram or ton. This is the step by step how to synthesize active ingredient for pharmaceutical industry. And then the important thing in the industrial development of drug is a synthetic methodology. Over the past 20 years, several scientists have been recognized with a Nobel Prize in the invention of synthetic methodology, such as asymmetric hydrogenation, asymmetric epoxidation, olefin metathesis, PD catalyzed cross-coupling. Innovation in synthetic chemistry provide opportunity to gain more rapid access to the biological active complex molecule structure in cost-effective manner. For example, in the synthesis of imipenem, this is analog for the penicillin, but the problem for penicillin is so many bacteria is already resistant for the drug. So synthesis chemists have to find the how to develop the analog. Before this, the cyclization to this beta lactam is very difficult because all of this functional group is very sensitive. That's why not easy. And then the synthesis chemists already discover using a ruthenium acetate as catalyst. This is a very soft catalyst, so can maintain the beta lactam ring. Another example, using the new methodology, ring closing metastasis in the synthesis of disease antivirus drug. Before this, to cyclize this compound is very difficult. But this new method using ruthenium catalyst and palladium carbon, this compound successfully cyclized to produce. This is the precursor for this antivirus drug. This is the new approach for the ring closing. Okay, beside the synthesis methodology in chemical synthesis, the synthesis chemists also approach the innovation also can we use like a biocatalyst. In the biocatalysis methodology approach, in 2018, Nobel Prize in Chemistry recognizing Franz Arnold for the directed evolution of enzyme. This is a very important methodology. Today, innovation in the area of molecular biology, bioinformatics, and protein engineering have enabled the development of biocatalysts with desired stability, activity, acquisition, selectivity. For example, for the synthesis of this drug, to cyclize this drug. This drug is very important to fight a virus because this drug can stimulate sting. This is a protein involved the activation of innate immune cell have been successfully synthesized. This is to stimulate sting, to produce chemical to fight virus. This is the synthesis route. And then another approach is this new approach, bioorthogonal chemistry. This the term of bioorthogonal chemistry is referred to any chemical reaction that can occur inside of living system without interfering with native biochemical process. The application of this method, including metabolic labeling for tracking purposes, enzyme activity profiling, drug target identification, and other biochemical application. For example, this one. This is a selective N and C terminal conjugation chemistry have been applied to identify antibody drug conjugation. This one, for this route, if we just to control the pH, the different product will appear. And then another approach in the synthesis chemistry is a technology to accelerate innovation, high throughput experimentation. in the high throughput experiment, the different parameter that determine reaction outcome, discrete variable like catalyst, reagent, solvent, additive, and the continuous variable, temperature, concentration, stoichiometric, can be holistically explored in the parallel. We can use the reaction with the robotic like that, robotic, and then we can run maybe around 100 experiment in the same time. So this is can save our time to identify. As a result, the synthetic chemist now has access to exponentially large amount of experiment data than ever before. Because before, for one synthesis, we do with one experiment, one route, one experiment, one parameter, one experiment, like that. For this approach, high throughput experiment, we can run all experiment together in the same time. For example, the optimization of the development of organocatalysts and selective and aza-micelle reaction for the commercial manufacture of the antiviral drug, letomorphia. This one, we use this technology, have successful to synthesize this drug. So from the library, we do the experiment, and then in this experiment, we try everything like the catalyst concentration, reagent, solvent, additive, and then temperature, and then another parameter, and then using the method is using this method. We save time and hello. Okay. Sorry, I have problem. Okay, this is the scheme how to synthesize with this synthesize the active compound with this approach. And then beside that, we can also use a computation method to analyze, to improve the method. Like this one, the advanced computation chemistry and machine learning in the past decade are delivering real impact in areas such as a new catalyst design or showing considerable promise in other such as reaction prediction. This one, we use a computation to predict the reaction. So we doesn't need to do the reaction, do the experiment in the laboratory. We can do first in using the computation model. This is, we can save our time, then we can save our budget. This one using computation. They analyze everything, and then we do the experimental. The optimum data we got from the computation, from the computational, and then we apply to the experiment. This one successfully synthesize this drug using the computation approach. And then for the future direction, we dreaming about how to design the molecule or design the method easier to edit the compound, the active compound. For example, this one, the lead scaffold for compound, we can edit. We can add a functional group here. We add group here, number one, or here, or we can modify this ring. This is aromatic, become the non-aromatic, and then we can edit like we writing, and then maybe because this word is no good, and then we delete, and then we change with another substituents. This is our dream. Because many many unsolved problem in the synthetic chemistry, like selective saturation and functionality of heteroatom, consist synthesis of high functionalized constraint by cyclic amine. This is our problem. CS of functionalized for this three substituted amine, selective functionalized of biomolecule, synthesis of non-canonical nucleoside. This is the problem is still in there. Is we have to improve this problem. The advantage for editing, molecular editing, is we doesn't need to synthesize this compound from the beginning, because today technology, if we want to put a functional group here, or we want to change from the aromatic to the unaromatic, we have to do it from the beginning. That we will we will spend more time to study this one. I think this one, the development of the drug is suitable with the sustainable development goal number 3, good health and well-being, and then we can also apply the industrial innovation and infrastructure. Sustainable development goal number 3 and number 9. Okay, thank you. I think that's all.
Okay, thank you so much, Dr. Agus, for your elaboration on the importance of synthetic chemistry in the pharmaceutical industry. And I think, yeah, it's a long process, as what I can understand from your presentation. It's a long period of drug discovery and also the development process from the plant itself until you get the pure compound, right?
Yes.
Yeah, and then something that I just wonder, the thing that you said, that 10 tons of U3, and then you only get 1 kilo Toxol.
Yes, that's true.
That one is just the traditional method, right?
Yes, traditional method.
But now you have something, you have different method, more innovative to get the sample, or how?
For complicated skeleton like Taxol, we still optimize how to synthesize that compound. But for the simple compound, we do it in the laboratory. But for complicated like Taxol is still difficult. We still use the semi-synthesis to produce that compound.
Oh, because it's a lot, right? 10 tons, yeah?
Yes, 10 tons. 10 tons.
Okay, all right. So I think we can open to the Q&A session. I will let Dr. Agus to rest 2 or 3 minutes break because you have just done your presentation. So I will scroll the question at the chat zone. Are you ready, Dr. Risa?
Yes, I'm ready now.
Okay, I think we have here. All right. Okay, first question from Dr. Warazarina. Okay. Assalamualaikum. What is or are the best method to extract secondary metabolite from microorganism culture? I think this one referring to Dr. Risa's presentation.
So may I answer now, or you?
Okay, yes.
Okay, I think the best method for extract secondary metabolite is nothing now. I think the same way we use the previous one, only using the ethyl acetate. We have already actually to do extraction. The previous one we use amberlite resin. We put some resin XAD18 put in the culture, and after that we grow the same with the fungus or actinobacteria. After 7 days, we collect the resin and we do like we clean the resin and hopefully hold the secondary metabolite from the culture we can get. But now I go back to the whole one. I only culture the microorganism and after that separate between the supernatant and the microorganism, and I extract from supernatant using the ethyl acetate because I don't want to use like cell. I don't want to use the cell because the secondary metabolite is very tiny, so it's not worth it to do purification from that. So we use only supernata now, but using the amber light is look like not significant result. The amber light is very expensive, so we go to the conventional method now. I think so. I don't have good answer. It depends on yours, your experience. Which one do you like it? I think yes. I try to go to like another university like USA, and yes, we go back to the first one now. But now today we try to do genetic engineering to get more compound from that. Okay, I think that's all for my answer. Hopefully,
I think there are several method, right? But
yeah,
it depends on the
method.
necessity and also budget. I think.
Yes, it's like efficient and the cheap one or advantageous using the method. From my experience, we cannot get very significant if we use the amber light. So we don't want to use the amber light now. So we can use conventional. Go back.
Okay. Okay, thank you, Dr. Risa. I think the second question also goes to you from Dr. Wan Razarina. Actually, what is the purpose of using anti-smash software?
Oh yes, anti-smash software is very good. Software, if we got the whole genome sequence, so we can predict biosynthetic gene cluster, especially secondary metabolite. So from the software, we can check what kind of secondary metabolite that we got, and after that, from this data, we can further analysis using the blast to make sure this is the real gene cluster or not. We can see maybe the mutation or something. So after we analyze, we can do like knocking out or knocking in from the fungus or bacteria. Hopefully we can the bacteria or microorganism can produce a new compound. So yes, this is the goal actually.
Oh, okay. I think maybe after this, Dr. Warazarina can have collaboration research, or maybe she
Very
can,
welcome.
yeah, she can contact
Very
Dr.
welcome.
Risa and colleague in Universitas Tanjung Pura to explore further on that. Okay.
Yeah.
Yeah. Next question. Okay. Next question we have here from Hanani Ruziman. I think this question can be answered by the two speaker. Assalamualaikum. Thank you, Doctor, for the presentation. I'd like to ask, how does this research contributes to SDG, specifically in SDG 3 and SDG 9? So maybe Dr. Agus can start.
Okay.
Okay, thank you. SDG. Wait, I get open.
So maybe I can help.
Okay.
Okay, you first.
Okay, Dr. Risa first.
Now, one of SDG three goal is to reduce the mortality as a result infectious disease like tuberculosis. So, in my presentation, we have already screened. The extract using like Mycobacterium smegmatis. Mycobacterium smegmatis can be used. It look like mimic Mycobacterium tuberculosis. So one of extract showing the activity for the Mycobacterium smegmatis. So this is a good candidate to develop as a candidate drug in the future if we can isolate and elucidate the structure for this. I think my presentation, the goal is drug discovery and the other drug discovery like anti-cancer or something else. And this is as very matched with the goal, the SDG 3 goal. I think
Yeah,
this is,
SDG.
yeah, and yes. Maybe Dr. Agus can
Yes, Dr. Agus, you want to add on?
add more?
Okay, for sustainable development goal number 3, I think is drug is very important for us all.
Yeah.
That's very important because without drug, I don't know what happened with us. So development drug is very important for good healthy and well-being because today like antibacterial drug is they say is a resist antibacterial drug because many antibacterial drug is resistant. Many bacteria resistant with antibacterial drug. So development of new drug is very important. This is can support the SDG number 3. And for SDG number 9, this is industrial innovation. This is drug development is under industry. So the development of drug is can increase the industry and innovation in the drug industry. I think that's all.
Okay, thank you so much, Dr. Agus. So next question from let me read. Okay, from Nurul Zawani Zulkifli. Assalamualaikum, Dr. Risa. What is the estimated time or period for each extraction of secondary metabolite to be completed?
To be what? Sorry?
What is the estimated time or period for each of extraction of secondary metabolite to be completed?
Completed, you mean, what do you mean?
The extraction of the secondary metabolite, how long it takes to complete the process?
It depends. For bacteria, non-bacteria, we can, after we grow one bacteria into the plus, we can harvest overnight for the normal bacteria like Bacillus, Pseudomonas, or Staphylococcus. But for Actinobacteria, we usually use 6 days. After 6 days, we harvest the culture and do some extraction. And so we can, if good the rotary evaporator, so we can get this day too. So the 6th day we can get the extract. And for fungus, it depends. Sometimes it depends what kind of fungus that we got. If we can extend the incubation time, like 5 days we can harvest. Like strobilurin, we can harvest 5 days. It depends what kind of strobilurin that we want to isolate. For example, strobilurin B can produce very good titer after we incubate 4 days, and the strobilurin A we can collect after incubation 6 days. It depends on our microorganism and the goal.
Yeah, correct. Because
It's very simple. It's very short time. If we extract from plant. So we should wait the plant can grow and all and so on, and maybe more than 1 year. So
It's a long process, but there is no specific time, I guess, because it
yeah.
depends on the what type of secondary metabolite and also what is the microorganism that you use, right? Okay.
Yeah.
Next question. I think Zawani. Okay. From Rafida Rasul. Assalamualaikum, Dr. Risa. Is there any known cases of fungicide resistance in targeted fungi?
Oh yes. Now many scientists reported some fungicide. Yes, some fungicide have a resistant, like aspergillus resistant about leconalgil, or strobilurin resistant powdery mildew, showing resistant toward strobilurin. Yes, many, but it's not. The rate is not high. If we compare higher compared with the bacteria is very high rate to resistant antibiotic.
Okay. I hope Puan Rafida Rasul satisfied with the answer. Next one. From Mr. Lo Cho Wai. Hello, Dr. Risa. How do you conduct field experiments using strobilurin? What is the concentration used?
Actually, for strobilurin, I only try to elucidate the biosynthetic pathway. So I put the gene responsible to do strobilurin biosynthesis, put in the Aspergillus oryzae, and after that only do some feeding experiment, put some benzoyl snake. So that's it. So I didn't do like biological activity. I think the question about that. So I don't care about the biological activity from strobilurin. So we only want to know what kind of gene or protein responsible to make a strobilurin. And we hope if we know the gene responsible to make strobilurin, because it's very weird to like rearrangement in biosynthetic pathway. So hopefully we can use the gene for another fungus to make a novel compound or novel secondary metabolite. That is the goal is for the drug discovery too. So it's like combinatorial biosynthesis. So yes.
Okay, thank you. And next question for Dr. Agus from Iqbal Haizat. Okay, Assalamualaikum and good afternoon. I'm Iqbal from URTM. I would like to ask a question regarding the method used in producing certain drug. As mentioned by Dr. Agus, the research will cost us a lot. What if we face a problem like irreversible chemical reaction, which will add the cost to our research? And how should we cater this issue?
Okay, thank you. For our lab, we doesn't go too far. We only study about the in the laboratory piece only. I think very difficult to develop one drug. This is very expensive. But that's possible. The possible because if we can find the collaborator from outside, maybe from industry, maybe that's possible. If we do by ourselves and we only use like FRGS grant, I think that's impossible for 44 million USD. I think it's impossible. That's why our focus in our laboratory is how to develop method, the good method for the synthesize, and then how to synthesize like a active compound from the nature like that. So we not go too far to develop one drug. That's very expensive. I think that's all. That's all myself.
Okay, one more to Dr. Agus from Intan Fadzil. Assalamualaikum, Dr. Agus Tono. If the drug has passed phase 4 of post-commercial surveillance and then only deaths and complications are reported, does the drug need to repeat the whole testing process?
Okay, for that case, I think the drug will withdraw from the market. FDA will release the letter to withdraw that product. We doesn't need to do the test for beginning, because that drug is like waste like that. So we save the drug. If maybe in the future we can apply the drug for another purposes like that. But to test again, I think it's impossible because they very costly to do from the beginning. So like a case for the Ebola drug, severe, that's not active, not good for Ebola. But recently, that drug is very effective to fight COVID-19 like that. Okay, thank you.
Okay, I think this is the last question to Dr. Risa. Okay, Dr. Risa, one more. Okay, from Shahira. Hi, Dr. Risa. Between basidiomycin and ascomycin, which one is the better secondary metabolites producer, because the gene structures look similar, but there is a slight difference between both of them? Does the difference affect the productions of secondary metabolites?
Actually, bulimia lutea is look like not from the ascomycin. So identification from the previous scientists. So so now we can refine bulimia lutea for Astrobilus lutea. So because the same basidiomycin, it should be the gene cluster is so like similar, even though there are some little bit different because this is different species. So that's why one of them is lutea, one of them is tenacellus. So maybe this is the answer.
Okay.
So
I think we have one more last question from viewers from the YouTube. From Shahira HL Moslami. I think any of the speaker can answer this one. For scaling up the fungal metabolites, do you prefer solid state fermentation or submerged one?
For me, I think it depends. I prefer using the not liquid fermentation, but some of microorganisms that we collect sometimes they can produce in the only solid fermentation. Only solid fermentation. For this case, we should do solid fermentation to isolate the compound. But commonly, I prefer using the liquid fermentation. It's easy, and we can get more. It's easy to handle, to extract, and it's easy to get more secondary metabolite compared using the solid fermentation. I think based on my experience, I don't know the other. Maybe the other people have different experience. Yes.
Yeah, Dr. Agus, what do you think?
I'm not working with the crop. the natural product to isolate active constituent from the plant. That's a little bit different because if we extract from the plant, we use a chemical to extract from the microbe. I think they will use a different approach like that. Thank you.
Okay, so I guess that will be the last question from the participant and viewer. That was absolutely a fruitful discussion that we had today with Associate Professor Dr. Risa Nofiani and also Dr. Agustono Wibowo. Again, I would like to wish thank you for both of the speaker. Dr. Risa Nofiani and Dr. Agustono, not to forget to all participants, not only from UITM but also from all other places who tune in and share with us those interesting questions. I hope the information shared during the session today will inspire our fellow researchers and students to generate more ideas in research towards achieving sustainable development goals and perhaps collaboration network between UITM, Universitas Tanjung Pura and other organizations as well. For UITM staff, link of attendance should be ready by now, I think, and also for the participant from outside UITM and also student, please fill up the attendance form to claim your ESTAT. And if you don't mind, Dr. Agus and Dr. Risa, can you share, if you are willing to share your email so that any student or researcher from UITM or from other organization, they can contact you if they are interested to explore more on secondary metabolites, synthetic chemistry or any related fields.
Okay.
Okay, I think Dr. Risa can be contacted at risa.nofiani@chemistry.untan.ac.id.
Yes, yeah, correct.
Yeah, or rnofiani@yahoo.com. And Dr. Agustono can be contacted at agustono@uitm.edu.my. Okay, I'm sure more ideas in research and biochemistry can be explored in order to support SDG goals in promoting healthy lives, well-being, promote comprehensive and sustainable industrialization to foster innovation. And we have now come to the end of the webinar session. On behalf of the committee, I would like to thank both of the speakers, Associate Professor Dr. Risa Nofiani and Dr. Agus Wibowo. Also to all the participants and students from Malaysia and all over the places for tuning into our live session today. Thanks again for your support and participation in this event. And I hope to see another speaker from Universitas Tanjung Pura and in the next webinar, insyaAllah. Until then, see you again and have a great day and stay safe, everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Dr. Risa and Dr. Agus.
You're welcome, Dr. Faiza.
Thank